This is part 3 in circuit design. I'm now going to discuss microcontroller load circuits. Microcontroller load circuits. Until now, we have talked about the load, and we've talked about a circuit that you might need to operate the load. In this circuit, you have a source of energy called a power supply. That power supply, using switches and wires, provides power to the circuit or the network. And we discussed how to properly arrange and select the proper values so that the right amount of energy will be received by your load component for it to operate correctly. And we use a 5-volt source of energy as an example. This is all good. I can operate the LED by switching it on and off. I can even play a game. Maybe I can push the button 20 times in 20 seconds. But there's a limit as to what I can do with a circuit like this, because it depends on me manually opening and closing the switch. There's a component out there called a controller, a digital controller. And with this digital controller, I can write a program that will turn its outputs on and off depending upon the logic of the program. These are called digital controller circuits. There are many types of controllers, but the two types of controllers in our project is the microcontroller, and we also have something in our project called the PLC. They both are digital controllers, but they are different in their applications and where they are used. I will start off by discussing a microcontroller. First, let's look at the setup for a microcontroller load circuit. First, you need a power supply, and the job of this power supply is to give energy to the microcontroller. So the microcontroller itself has a need for a positive and a negative to operate. So you would join your circuit. So basically what you're doing is you're passing energy from the power supply into the microcontroller. Now the microcontroller will decide when this energy will be switched on and off. That way, you do not have to manually turn the power supply on and off. You can write a program, and the program will determine when to turn the power on and off. I may decide that I want the power to be off, and then at a certain time, I want the power to come on. And then maybe after 10 seconds, I want that power to go back off again. And you can do that by writing a program. Now, normally I would not draw the power supply this way, but I'm just using it in this example to demonstrate that energy here is being passed to the microcontroller, and then the program inside the microcontroller will decide when to release that energy out. So this becomes your new power supply. But this power supply is like automatic. Now, what is the typical values for this power supply or electrical characteristics? Well, that depends on the microcontroller. And again, you would go to the data sheet and you would research that information. In this example, we can assume that most microcontrollers can supply about 5 volts as long as the current does not go above 20 milliamps. This is how much it can source. Now, the one thing about the microcontroller is that it can do two things. It can provide an output, we call that source, but a microcontroller can also do something else. It can actually do something called sync. It means it can receive current. Unlike the power supply, current only goes out. It does not go back in. But since I can control the value of this voltage, I can make it 5 volts, or I can make it 0 volts. Then I can use this as a power source, or I can receive current. And I can receive up to 25 milliamps of current without any problems. What that means is I can put another circuit over here and actually push current back into the microcontroller. That's a very important advantage in circuit design. But going back to our original problem, we have an LED again. And this LED is rated at 1.7 volts and 10 milliamps. Now the first question you have to ask is this: can this provide 10 milliamps of current? The answer is yes, because this microcontroller can provide up to 20 milliamps without causing any problems. Do you recall the diagram that I drew earlier, which says that as the current out of a power supply increases, the voltage will remain steady up until a certain point, and then finally it will begin to drop. Well, for this microcontroller, that current is 20 milliamps. As long as the current is in this area here, then you can be confident that you will get the 5 volts. But if you keep on taking more and more current from this microcontroller and it goes above 20 milliamps, then the voltage out of the microcontroller will begin to drop. In our case, we're only going to be operating the LED at 10 milliamps. Therefore, we should be very comfortable that our microcontroller will be safe. So for all practical purposes, we have a circuit that's very similar to the circuit that we had before. where we have a power supply of 5 volts. We have a load which is rated at 1.7 volts and 10 milliamps. And we would just have to connect a resistor to protect the LED from receiving too much. So we can use that same information to complete our new design. Energy will come out, current will flow through the resistor, through the LED, and it will return back to the negative part like a normal closed circuit. This becomes your new automated power supply. And the resistor, you can use the same value as before because you have the same 5-volt power supply, at least when it's on. Now, when the microcontroller decides to turn this off, then the voltage here will be 0. And if the voltage here is 0, then no current will flow through the circuit and the diode will be off. So let's summarize here. We know that loads are basically components that requires an energy source to operate. Some examples of loads include LEDs, you can have buzzers. These are components that make an annoying sound. You can have speakers. You can have something like motors. Relays are good examples. You can have lamps. All these are components that require some type of energy source to operate. Some of them are AC, some of them are DC, and some of them can be used AC and DC. Some of them only can require current in one direction. Others can operate with current in both directions. And as usual, you would need to study the data sheet to learn the correct electrical operation of the components. We discussed about loads, and then we said, what do we need in order to make it work? And what do we mean by make it work? It means that we are applying the correct level of energy so that the device can operate in its natural state. For lamps or LEDs, that means it will create light. For buzzers, that means it will create sound. For speakers, it will also create some type of sound. For motors, that means it will create some type of rotational movement. For relays, that means it will operate a switch. It will open and close a mechanical switch. And lamps, like LEDs, will create light, but a lot of light. That's what we mean by make it work. Finally, we said this kind of system here is operated mechanically. But what if we wanted the LED to be more active? We wanted to have more options for operating the LED. Then this is when we would substitute or replace the power supply with a microcontroller power supply. Now, by writing special program steps, we can operate this LED in special ways. For example, we can decide that we want the LED to be off for a little while and then turn on for about 10 seconds and then turn off. And we would go through the same calculations as we did before, treating the microcontroller like a power supply. The major difference between the microcontroller power supply and a normal power supply is that with the microcontroller power supply, current can flow out of the microcontroller when it's 5 volts, and it can flow into the microcontroller when it's 0 volts. That's a very important part. In this state, we say it is acting as a source of energy. And in this condition, we say it's acting as a sink of energy. It's receiving current. And that becomes very important. The microcontroller has its own power supply, and we say that the microcontroller will first receive energy from this, and then it will pass that energy out to the next step according to the program that you have written. That was part 3 of microcontroller load circuits. Part 4, I'm going to discuss a situation when the microcontroller does not have enough energy to operate the load. If it does not have enough energy to operate the load, then you need to add an additional circuit called a driver. And we will discuss more of that in the next video. Thank you.